Okay, so section 9.3, the parabola. I'm going to talk about the parabola as a conic section. We've seen equations for parabolas multiple times now, but we've never seen it as a conic section. So I'll add a page like I've done before, just sort of draw again how the parabola comes to be. And you can say, it's kind of telling it does make sense, because for the hyperbola, I already told you that the hyperbola is similar in shape to the parabola, though it's not the same type of curve. The parabola happens when you cut a cone parallel to one of these lines. So one of these lines here, sorry about that, let me go back. This line here, right, you see that? If the plane you cut the cone with is parallel to that, so say a cone like that, draw it. Right, so you're cutting the cone in this exact angle. The curve that you get is the parabola here, right? So that's the parabola. So if you look at it from this angle here, what you're seeing is a parabola, right? So that's how you see parabolas as conic sections, okay? So let's get to the objectives. We want to be able to graph them by looking at equations, to write their equations when the vertices are not at the origin as well, to solve applied problems, to identify conics using all we know so far about all three conic sections that we've seen: parabolas, ellipses, and hyperbolas. Okay, so let's get to it. So a parabola is the set of all points, that's the definition, right? Before I get to the equation, is the set of all points in a plane that are equidistant from a fixed line. So just like we said, we had two foci for both the ellipses, for both the ellipse and the hyperbola. For the parabola, you have a single focus, right? And here's the focus. And you have one line that's the directrix. So you pick all points such that, let's say this point, if I measure the distance from the parabola to this focus, that distance has to be the same as the distance of that point to that line. So that's the closest point in the line, right? The closest distance from your point to the line. So this distance has to be the same as this distance. So all such points, all points to satisfy this property, are points in the parabola. That's how you define it, okay? It's important that you remember this property, because in some applied problems, that's what they're going to tell you. They're not going to tell you that the trajectory or the shape, the curve that you're using the parabola, they're going to tell you this property. They're going to say, oh, consider all points that are equidistant from a fixed line, right, and a fixed point. So they may say that. And you have to identify that that's a parabola. But anyway, here's the standard form of the equation of a parabola when the vertex, right, the vertex being this point here, is at the origin. So it's either y squared equals 4px or x squared equals 4py, and that depends, right? So the way I think about it is, what should be squared, right? The parabolas we've studied so far, which come from quadratic equations, they come from things that look like this, and x squared is what shows up, never y squared, and then they're either concave down or concave up. So that way I know that when x is the thing that is squared, I know my parabola is vertical, so either concave up or concave down. For it to be horizontal, I want the other thing, so I switch x and y, switch their places. So that's how I remember which one is which. And the equation of the directrix, you got to remember, is 4 equals to minus p, is minus p, either x or y, right? Or positive p, depending on how that goes. You can change the sign. Rather, it's always minus p. P could be negative, and then minus p would be positive, right? That's the point. And then the focus is always p in the direction of the axis. So you decide whether it's vertical or horizontal, and then you move p towards the inside of the parabola from the vertex, and that's the focus. You move P towards the outside of the parabola, and that's where the directrix should be, right? The directrix line. So let's see this example. Find the focus in the directrix of the parabola given by y squared equals to 8x. So I know this is y squared equal to 4px. So because y is squared, I know this is not the parabola I'm used to dealing with. So the parabola is horizontal and not vertical like I'm used to, because y is squared, not x. Okay? And now I know that 4p equal to 8, right? 8 equals 4p. So then p equals to 8 divided by 2, meaning p equals to 2. So if I were to draft it, if I were to graph my parabola, y squared equals to 4x means, so it's horizontal, and because 8 is positive, then it's opening to the right. So it's like this. Okay? So to find the focus, I move p in that direction. So it's 2, 0. In the directrix, I move p in that direction, -2, and it's a line this time, right? So then the directrix will be x equal to -2, right? The vertical line. And remove this equal sign here because that doesn't make sense. And the vertex, not the vertex, the focus will be 2, 0. Okay? That's exactly it here. So what they say is that to graph it, we'll use 2 points that are directly above and below the focus. So they want to know, if I go back to the graph that I had before, they want to know this point and this point, right? And all that tells me is that I need to plug in x equals to p, right? Or x equals to 2 in that case. Right? So remember, y squared was 8x. Sorry, that's wrong here. That's 8, 2. Well, let me continue. So x equals to 2 is what I want to plug in for to find these 2 points. So y squared equals to 16. So that means y equals plus or minus the square root of 16. So y equals to plus or minus 4. Okay. So x was 2 because I plugged in 2 here. So that means 2, 4. And 2, -4 are the points that I will add. So that's what I do here, right? I have my focus. I have the directrix. I have these 2 points. And I recommend that when you graph your parabola, that you add a label to these points here, right? So this is 2, 4 and 2, -4. Because you can see if I'm lazy or not very accurate in drawing my line, this is not gonna look very aligned to 4 to -4. So it's always a good idea to label your points. Now, this line here, this vertical, not line, this line segment, right, connecting these 2 points, this has a name. And this is called the latus rectum. We'll see that later. Yeah, there you go. So it's a line segment that passes through its focus and is parallel to the directrix. It has endpoints on the parabola. The length of the latus rectum for the graphs of the shape is absolute value of 4p. So it's absolute value of this thing here, right? Okay. So it's always going to be the same value. So here's the example. Find the standard form of the equation of a parabola with focus here and directrix x equals to -8. So if I place this here, so 8 comma 0 lives here. So this is the focus. I'm not writing focus very well today. And then the directrix is x equals -8, so it's the opposite direction. So here, it's the directrix, vertical. So that means my parabola looks like this. And that's the vertex. So I can see that the distance between the vertex and the focus, right, is 8. So I can see that p equals to 8. Okay, because my parabola is horizontal, then y squared equals to 4px, right? It's horizontal, it's not the usual shape of the parabola, the shape that I used to do with quadratic equations. So y is squared, not x, right? Because it's unusual. And then p was 8, so that's y squared equal to 8 times 4 is 32x. So that's the equation. Found it. Okay. If I wanted to find, let's see the second example. Yeah, you see, we're good. Not the second example, the second page. If I wanted to find the latus rectum of this thing, I look at the focus. So let me do it in red this time. I plug in x equals to 8 onto my equation. So what's that? 32 times 8. So it's times 2, 3 times, right? So 64, 128, 256. So y squared equal to, so y equal to plus or minus the square root of 256. Sorry. Also messed up the square here, right? Okay, so what's the square root of 256? Is it 16? 6 times 6, 6, 3, 6, 9. Yeah, that's correct. So 5, 1, 2, yeah, 256. So y equals plus or minus 16. So the 2 points on the latus rectum, if I were to extend this, right, they are eight comma 16, 8 comma minus 16. Always a good idea to place these 2 points when you're graphing them. When you're graphing the parabola, always a good idea. Okay. All right. So when the parabola is shifted, not centered at the origin, same thing happens. You just like before, right? Minus k minus h with this new vertex. So you just replace x with x minus h and y with y minus k. And then you graph it exactly the same way. You're moving, right? P to the left, P to the right, or P up or P down. But the trick is you start, instead of starting from the origin, you start at HK, which is the vertex, okay, rather than the origin. Okay, so I'll skip over this. I'll let you look over this example here and figure this out on your own. It's the same idea, like I said, right? You start from the vertex this time, right? And once you find P, you move P up or P down or P left or P right, depending on starting from the vertex rather than from the origin. So I'll let this be. Let's solve this application, which is much more interesting. So an engineer is designing a flashlight using a parabolic reflecting mirror and a light source. The casting has a diameter of 6 inches and a depth of 4 inches. So here you go. So we know that we have a parabolic mirror. So the shape of the mirror is a parabola. The casting, the shape, right, is 6 inches in diameter. So this thing here, right, the diameter of the circle here is 6 inches, and the depth is 4 inches, exactly how the picture indicates. So what is the equation of the parabola used to shape the mirror? And what point should the light source be placed relative to the mirror's vertex? Okay, so let's see that. Let's first find the equation of the parabola used to shape the mirror. So let's graph it. Let's first place our parabola in a coordinate system. So always when the vertex is at the origin, it's easier. So place the vertex at the origin. So I have 6 inches, 4 inches. So that means if I move, so remember 6 is the total. So it's 3 to the left, 3 to the right. So that's 0.3. That's -3. And because the depth will be 4, that means the coordinate here is 4, right? It's not very good symmetry there. So I'll correct my points. So that's 0.3, 4. This is -3, 4. Okay? Okay, so I know these. Give me a second. I know this is a parabola centered at the origin, so I know that it's vertical as well. So I know it's just like I'm used to. X is squared, not y. So I get that vertical, excuse me, x squared equals to 4py, right? So the opposite as before, x is squared because vertical is something that I'm used to, and x squared is something that I'm used to. Now I want to find the value of p, so I can pick one of these points and plug them in. So x equals to 3, y equals to 4. So that means 9 equals to 16p. So p is 9/16. So that means the equation of the parabola is x squared. So p equals this thing, right? So 4 times 9/16y. You can cancel this to get a 4. So x squared equal to 9/4 y. So that's the equation of my parabola. Okay? Okay. The question now is, at what point should the light source be placed relative to the mirror's vertex? And this is the key point here. So just like before, the focus, the word focus, is not meaningless, right? It means exactly what you'd think it is. So remember for the elliptical pool, I think I mentioned that anything that reflects off of the ellipse comes back to one of the foci, right? And that's the point here too. So if you have a parabolic mirror and you place a light source here, these light rays that are weird, so this happens with headlights in cars too, right? So you have parabolic mirrors, you have a light source. Some light rays go straight off, and this is great, this is what you want. But some of these light rays, they go into the mirror, that's why you have a mirror there. And if this is placed at the focus, then they will be reflected straight out to sort of intensify the light. All light rays will do this. Okay? So that's one of the usefulnesses of parabolas. So if the light source is at the focus, and the opposite also works, right? If you want to heat up something using a mirror, you want to place that something in the focus, because all light rays that come straight, they concentrate on the focus. But this case is the opposite, right? It's the light starting at the focus and then being reflected out. So you place it on the focus. So the light source should be placed on the focus. In the equation of the focus, because it's a vertical parabola opening up, right? It's you move p up, right? So you move p up from the origin, you know p So the focus is p comma, so 0 comma p rather, right? X equals to 0 comma p. X equals to 0, y equals to p, I mean 0 comma, and p is 9/16. So what's the unit of measurement? This is inches. So at what point should the light source be placed relative to the mirror's vertex? So it is, which is located 9/16 inches above. So I'll say directly above, just to be clear, the mirror's vertex. Okay, that's how this works. All clear? It's another important property for parabolas. We won't use this. Okay, now, if you have an equation for a conic section that you don't know what it is, you want to make sure that you're able to identify that without having to complete the square. If you want to graph the conic section, you have to complete the square to find exactly what the vertex is and exactly what the values of p and everything else, or a and b, depending if it's ellipses or hyperbolas. Find those values. But if you're given an equation of this form and you want to know what it is without having to graph it, that's very important. So what you're going to look at, first thing you want to look at is the coefficients of x squared and of y squared, right? So if these two coefficients are equal, okay, then, so first of all, this is the first important thing. They can't be both 0. So these two guys cannot be 0 at the same time. This is necessary for this to be a conic section. Otherwise, it's just a plane or something, or a line, whatever. But okay, if they're not both 0 and they're equal, it's going to be a circle. If one of them is 0, so again, they can't be 0 at the same time. So one of them is 0, the other is non-zero. So let's say only x squared shows up, but y squared doesn't show up, then that's a parabola. Okay? And if a and b are both have the same sign, right? That's what it means with the product positive. The product is always only positive if they both have the same sign, but they're different. Then that's an ellipse. And if the product is negative, they have different signs, then that's a hyperbola. So you recall that happens on the basic equation of hyperbola too, right? You see that y squared and x squared have different signs, so that's why the product is negative. For ellipses, that's the equation of an ellipse, right? So then x squared and y squared have the same sign. They may be different, right? A and b, little a, little b may be different, but they have the same sign, so it's an ellipse. If they're equal, right, then it's a circle. And for the parabola, it's obvious, because if either a or c equals to 0, then only x squared or y squared shows up and not the other one, so it's a parabola for sure. So let's see an example of how to apply this. Identify the graph of each of the following non-degenerate conic sections. So you can see already that x squared and y squared have the same coefficient. So a equals to 1 and c equal to 1. So they're equal. So that's a circle. Right? So now a equal to 0, meaning x squared does not show up, right? But y squared does, so that's a parabola. That's pretty much it. Okay? So that's it. I'll stop here now. Make sure you should be able to finish the homework assignment now. Thank you for watching this.